energy. Right? So these are the things actually that we need to be discussing today, right? So after that actually, if time permits, I am going to discuss Gauss theorem as well, right? So here, so till now actually we learned the Coulomb's law and the effect of Coulomb's law, and then how to find out the electric field intensity with the help of Coulomb's law, right? So that's what we learned till now. So, but there is one important point, that is the potential, right, which we will be using in our entire electrical engineering or electronics engineering. This terminology actually is very, very famous, the potential or the voltage, right? But nobody talks about electric field intensity, right? Though the effect is just because of the charge, you are not talking in terms of electric field intensity. You are talking always in terms of volts. So these many number of volts I have applied to a circuit, right? Or this is the transmission line voltage. That is the terminology we use, right? Now coming back to what is this potential or what is this voltage? What is the voltage? So how do we define voltage? Right. So here actually, so if there is a charge and because of that charge actually, so there is an electric field intensity that is associated with any charge of magnitude Q. Right. So this is the charge. Now this charge is having an effect which we call it electric field intensity. Yeah, yes, that's exactly what you said is correct, Hafiz. So this is the electric field intensity. But from here actually we derive something called voltage or the potential, and which will be rigorously used everywhere or in every textbook or everywhere wherever we thought about electrical engineering or electronics engineering, right? So this is the term we use. So why we use that is, the greatest thing about this is a scalar and this is a vector. This is the only reason. This is the only reason why we brought something called potential or something called voltage. There is no other reason. But actually we completely forgot about this, right? We completely forgot about this. So in every textbook, if you open, maybe it is Millman-Hawkins or actually maybe network theory by Van Valkenburg or power systems or power electronics or control systems, anywhere you talk about only with the voltage. Only in EMF actually we talk about electric field intensity. Right? So I told you EMF is a physics part. So from the physics actually, whatever is needed by the engineering people, that will be derived and left it over there. So this is where actually we are deriving it. Got it? So this potential, the beauty of this potential is scalar. So that means you can add this way. So 2 volts plus 3 volts if you apply, so effectively I am applying 5 volts. This is how we calculate it because this is scalar. But if I say E is equal to 10I plus 20J, this is E1, and E2 is equal to 20I plus 30K, then E is equal to E1 plus E2, then you cannot straight away add, as if like we have added in this manner. Yes or no? This level of complexity brought into a small complexity or most easiest way of approaching the problem, right? So this is how actually we are converting it, just because we derived something called voltage or something called potential, right? So now actually the important properties of potential is it's a point function. It's a point function. This is one of the important property. Which means is, suppose I have a charge here. I have a charge here. Now, this magnitude is Q. Now, the electric field is associated for this particular charge at a distance of R is, let us say, E. This is the electric field intensity which is coming radially from the charge, right? Now, to bring a point charge from here till this particular point, right? I need to be doing some external work. Yes or no? So I have, let us say, I have a charge Q1 here. Now I am bringing that Q1 towards this particular Q. For that, actually, as per Coulomb's law, it will try to oppose if it is a same sign, and it will try to oppose it in a opposite direction, and then you have to do external work to bring this particular charge to here. Yes or no? In opposition to the electric field intensity that is produced by Q1. Right? But suppose if I am trying to move this charge in this direction. So from here, let us say I have Q3 here. Now I am trying to move this Q3 till this point in this direction. How much work I should do? Maybe certain quantity of work we do, but actually I am moving this charge in a complete rotation till this particular point to here. Now how much work I should do in bringing this entire charge from here to here? How much work I should do in moving the charge Q3, so from this particular point, rotating this entire circle and bringing back to the same position. So yeah, that's exactly what you said is correct, Hafiz. So 0 joules of work actually I will be doing. I am not doing any work in this case. Why? Why? Why I am not doing any work in moving? Work done is constant. Yeah, if the effective distance is 0, then there is no work done, because work is nothing but force into displacement. There is no displacement there, right? So that is anyway physics property. But here in this case, if you notice, the electric field intensity is in this direction. Got it or not? Now here actually, this is the electric field intensity direction. Right? Now, so now actually this particular charge, right? It is trying to move in this direction, but actually I am trying to move exactly perpendicular to that particular line. So am I doing any work? So if I am trying to move a particle which is perpendicular to the electric force or electric field intensity direction, so am I doing any work? No work, right? So that's why, so in moving this entire circle, actually there is no work done at all. That means, suppose if I move this particular charge from here to here, let us say I have another circle this manner. Now, at this particular point, so the electric field intensity here it is E1 and here it is E2. Now actually, if I am trying to move from here to here, will I be doing any work or not? Yes, definitely, right? Because I am moving against this particular electric field intensity, which means that this is what we call as the equipotential line. This circle is called equipotential line. That means there is no potential difference between this point and this point, because the electric field intensity is same, whatever is there here, right? Same electric field intensity there is here also. Even here also. Any point on this particular circle, the electric field intensity is same. Right? Electric field intensity is same. Now actually, suppose, so if I am trying to move this particle, I am not doing any work extra in moving that particular particle, right? So that's why this line is called as the equipotential line. Equipotential line. And if I am trying to move in this direction or actually in this direction, definitely I will be doing certain work. That means the potential at this particular point and the potential at this particular point is different. Got it or not? The potential at that particular point are different. That means there is a potential difference between this circle and this circle. Got it? So, and one more important property of this potential is it's a point function. So I have already written. So what it means is the potential at any point, actually, so the potential at this particular point, right? Let us say The coordinates are x1, y1 and z1. These are the coordinates of this particular point. Definitely there is a potential associated at this particular point because of this charge, which is having an electric field intensity of E. Now definitely, suppose if I take one more point here on the outer circle, the coordinates, let us say x2, y2, z2. These are the coordinates. And here the potential is different. The potential is different from this particular point. And on this particular entire circle, the potential is same. On this entire circle, the potential is same and is equal to this particular one. So, but here to here, there is a difference. Got it or not? Which means that is, the potential is dependent only on the xyz coordinates of that particular point. Got it or not? So, V is a function of, it is dependent on the xyz coordinates of that particular point. Got it or not? Right? That means if you wanted to find out the potential difference between this one and this one, then phi of x2, y2, z2 minus phi of x1, y1, z1 is the actual potential difference between the 2 points x1, y1, z1 and x2, y2, z2. Got it or not? So potential you can find out just by knowing the coordinates of that particular point there itself. Got it or not? But in case of electric field intensity, right? So the way the lines are distributed, right? That depends on the path because it's a vector. But here in this case, it depends only on the point. Got it or not? If you wanted to find out the work, right? So how do you do? Suppose I have a block here. Now actually I am trying to apply a force in this particular direction, right? Now the direction of this particular force is very, very important to find out the effective force that got applied on this particular block, right? Now actually if it is inclined, let us say this is making an angle of theta, then actually F cos theta is the actual force that got applied there, which is in this particular direction, horizontally or parallel to the block, right? Now if I am trying to apply the force in this direction, there is no movement in the horizontal direction, obviously, right? That means, though the magnitude of the force is same, the way I am applying is very, very dependent, right? So the way I apply is quite dependent to move this particular object, right? So this direction, right, actually deciding rather than the magnitude, or actually it's both, right? But here in this case, there is no direction associated there. It is just a single point where it is located in, right? So that's why it's a point charge, or sorry, it's a point function, right? It's a point function. Potential is a point function. So because of these reasons, actually we have defined something called potential, which is very, very important for us from now onwards. Got it? Okay. Now what is this potential? So again, the fundamentals are same. So it will come only from the Coulomb's law again, right? So Coulomb's law, what it says is, so F is directly proportional, or F is equal to Q1 Q2 by 4 pi epsilon R square R cap. So this is the Coulomb's law, what it says, right? Now, electric field intensity because of any charge Q1 is equal to Q1 by 4 pi epsilon R square R cap. This is the electric field intensity, right? Now, I have a point here, point charge of magnitude Q1 here. Let us say I have a point charge of magnitude Qt is here, right? Now the electric field intensity associated with this particular point charge is E. So E1, right? So let us say this is E1. Now I am trying to move this particular this particular charge Q2 against the electric field intensity. Then what is the effective force that I should be applying there? What should be the effective force that I am applying? to move this particular charge opposite to this E, what is the force I am applying? I am expecting answer. What should be the force that I should apply on Q2 to bring towards this particular Q1? So it is essentially the repulsive force that is happening on this particular Q2 because of Q1, right? Which essentially means that the electric field intensity into Q2. So this is the effective force. Yeah, Q1 Q2 by 4 pi epsilon r square, which means that, so if I express in terms of E, so this is the same formula, E is this one. But I divided E1 and Q2, that's all. Right? So E1 actually this entire part excluding Q2, right? So that is the effective force and in the radial direction. Got it? And in the radial direction. Now, suppose let us say I am trying to move this particular particle for a distance of dl. So that is an elemental length. I moved that particular dl, right? Now, my work done is equal to F dot dl. Yes or no? F dot dl. Got it or not? So why I am taking this? Now, this F is having a direction of r cap. And this dl will be a vector. Why I am taking this as a vector is, now actually I can bring this particular charge in this direction, or actually my electric field intensity lines are going in different ways in all the directions. Now I wanted to move in this particular direction Q2. But the electric field intensity, if you notice, at every point the electric field intensity direction is different to the direction where I am moving in. Yes or no? Got it or not? But effectively, how much effective force I am applying is dependent on the direction what I am moving in. Suppose, rather than this direction, I will give a better example. Suppose my electric field intensity lines are in this direction. So this is the electric field intensity lines direction. Now, I am trying to move a charge which is at this particular point in this direction. Got it or not? So if I have to move, then let us say it is making an angle of theta horizontally. Theta horizontally. Which means that it is making an angle theta here, theta here, theta here, and always actually it makes the same angle because these are all parallel lines, right? Now effectively at this particular point, let us say, so this is a small triangle, right? And the horizontal component is cos theta. So this length is, let us say L1, that length. Hypotenuse length is L1 for this particular small triangle. Now L1 cos theta is the effective horizontal length that got moved, right? So this is L1 cos theta. So that is the effective length that I moved, which is exactly opposite and parallel to the electric field intensity line, right? Now here actually this is L1 cos theta. Now if you take this another triangle, then it will be L2 cos theta. Got it or not? If I take another triangle, it is L3 cos theta, which means that effectively how I am moving exactly opposite to the electric field intensity is decided by this cos theta and the length. Got it or not? That is why, so this will come as a, dl will be a vector and the cos theta factor, to incorporate the cos theta factor, we brought dot here, dot product. Got it or not? Right? So dl will be a vector and the dot product comes here, and whether it is a F or E, it doesn't matter. Definitely the dot product has to be associated there. So that gives the effective movement against this electric field intensity. Got it or not? Even if you are moving slantly, but effectively how you are moving is against the electric field intensity, but the magnitude of the length may be different from this particular length to the horizontal length. Right? So that effective length we need to be calculating, hence you are getting in this manner. Now actually you are moving against the electric field intensity. That is why we take this as the minus sign, minus F into dl, f dot dl, right? So this dl actually I have explained earlier. For Cartesian coordinates how it is, for cylindrical coordinates how it is, and for spherical coordinates how it will be, I have clearly explained in the previous classes, right? So you have to adapt appropriately there, right? Now this f is equal to minus E into dot dl into Q2, right? So this F actually I have substituted here. This is the work done. Now this work done for moving a charge of magnitude Q2. But rather than that, if I move a charge of magnitude 1 coulomb, which means that my Q2 is equal to 1, right? Or W by Q is equal to minus E dot dl. E dot dl. So W work per unit charge is nothing but the potential or the voltage. Got it or not? So this is actually moving an elemental length of dl against the electric field intensity of E. So this is the actual work done. Yeah. So negative sign actually we are taking because we are trying to move opposite to the direction of the electric field intensity. We are doing external work on that, right? Got it or not? So we are doing external work opposite to the electric field intensity, or we are trying to accumulate energy to that one, which essentially means that if we release it, it will revert it back. Got it or not? Suppose this chalk piece is there. Now actually from the ground actually I have lifted till this particular point, which means that I have given some potential energy to this particular chalk piece. If I leave it, automatically it will fall down, right? It's exactly I am trying to accumulate certain potential on this particular electric field intensity for the charge Q2 by bringing nearer to this Q1. Got it or not? If I leave it, automatically it will throw away. That means you are energizing and keeping it there. Got it or not? So that is the potential, right? The person who is having ability to do certain work, right? That is what we call as the potential of that particular person or the ability of that particular person. Even here, the charge actually it is accumulating certain energy and keeping it there, which means that it is ready to do work back. So the accumulation part is the negative sign, opposite to that one we are doing, right? So anyway, whatever we are going to discuss, right, we have to make sure that law of conservation of energy has to be satisfied. So even here also, energy never be created, not destroyed. So the same principle even applies here. Got it or not? So this is actually the potential. Now actually, if I move charge from a different location to, let us say, this point is A and this point is B, or actually this point is A and this point is B. I am trying to move this particular direction against the electric field intensity, which means that I am moving from A to B. So this is actually the total voltage or the potential difference between this point and this point. Got it or not? Understood the potential concept? Right? So this is about the potential. Now how to calculate potential for different kinds of configurations we are going to see now. So the new formula along with the Coulomb's law is now it is the potential V is equal to minus E dot dl from initial position to final position. Got it right? So this E dot dl actually the way I have explained, right? That's what we call as the line integral. So along the line actually we are doing the integral, hence we call this as the line integral. Got it? So this is the line integral. Now let us say I am taking a point charge of magnitude Q, right? Now to find out the potential at any point because of the point charge, let us say, so this is the point I am considering for a distance of R. So what is the potential at this particular point if you wanted to calculate? So you will be calculating V is equal to integral, right? Now actually the potential difference we always calculate. If you wanted to calculate the potential itself, you have to bring the point charge from infinite location to that particular point. Got it or not? This concept. Suppose actually this initial position is at infinite, which means that I have a charge here. Now I am trying to bring 1 coulomb charge from infinite to till this particular point A. So let us say this point is A, right? So here, if you wanted to find out the potential at this particular point, not the potential difference, potential at this particular point means the potential difference from this particular point versus infinite. So this is the potential. So minus, so E is nothing but Q divided by 4 pi epsilon R square R cap. This is E, right? And this is minus. And started at infinity. And then coming to the point where it is equal to, maybe let us say A. So this is the length A, the radius A. Now Q by 4 pi epsilon R square into dl. So this is the dl, right? This is a vector I told you. Now in case of spherical coordinate system, dl we assume to be how much? What is the dl expansion in case of spherical coordinate system? Why we are taking spherical coordinate systems is because this electric field intensity is calculated by assuming spherical coordinate system. Hence this R is in spherical coordinate radius. Got it or not? Is it clear? Yeah. So dl is equal to R cap, not really. So what is this dl is? So I have explained earlier, in case of Cartesian coordinate system, this is dx into I plus dy into j plus dz into k. This is Cartesian. In case of cylindrical coordinate system, this is dr r cap plus r d theta cap plus dz into k cap. In case of spherical coordinate system, this is dr into r cap plus r d theta into theta cap plus r sin theta d phi into phi cap. So this is the dl value. I hope you remember it. I have explained when I explained the initial classes, right? Yeah, so yeah, that's correct. So but actually, so you are directly taking dl as r cap. So but actually why I said wrong is you need to take dr into r cap. Dr part you left it. So this is very, very crucial for us because actually there is no dr in this integral, right? So this is equal to minus integral infinity to a q by 4 pi epsilon r square into r cap dot this dl actually you have to assume in the spherical coordinate system because this E is calculated in a spherical coordinate system. Now this r cap is there. So the dot product of this dl into r cap, all other components except r cap components are going to vanish because these are the dot product and all are actually perpendicular in direction. So this is r cap, this is r cap, means these two are parallel in direction. Hence the angle is 0, cos of 0 is 1, which means that, so this is r dr. R cap product will be 1. And then r cap into theta cap, because these two are in perpendicular directions, it will be 0. R cap into phi cap, these two are in perpendicular directions because, so hence it is 0. Right? So only thing left over is, so this r cap will go out and it will be dr. Here the beauty comes. Now actually this is a scalar. This is a scalar. So because of this nature only, we are calculating all these things, right? Now it is a scalar, which means that, so minus q by 4 pi epsilon integral infinity to a and dr by r square. What is the integral of this? Minus 1 by r, right? So minus will get cancelled out. So this is equal to, so q by 4 pi epsilon 1 by r, so a to infinity. So this is equal to q by 4 pi epsilon 1 by a minus 1 by infinity. So this is equal to q by 4 pi epsilon a. There is no vector quantities here, right? So this is how we calculate the potential of any charge at one particular location. Understood? Ranjana, any questions on this? Okay, fine. Okay, you may go through the recorded videos. In case if you have any questions, you can ask me tomorrow. Okay. So this is actually the potential calculation, right? So this now actually we calculate the potential difference. So the potential difference is nothing but rather than moving from infinite, if we are trying to move from B to A, so that means I have a charge here. Now actually I am trying to move from this particular point to this particular point, right? From this particular point to, so this is, let us say, at a distance of B from here, and this is at a distance of A from here. Now actually you might have noticed here the direction is not exactly parallel to the electric field intensity line. So at an inclination of some angle I am moving in, got it or not? Right? So this B may be here or may be here. So this A is here. Now actually I am trying to move along this particular direction. So this point is at a length of B and this point is at a length of A. Now these things, like actually even though you are not moving against this electric field intensity exactly in the same manner, still actually these points are taken care because of the dot product here. I explained how it is, right? So because of this dot product, actually whatever may be the point you consider, you just needs to change is V is equal to minus integral B to A Q by 4 pi epsilon R square R cap into DL. Got it? So this will be the same procedure. So once you finalize it, so the upper limit is Q by 4 pi epsilon into 1 by A minus 1 by B. So exactly in the same manner you will have to calculate the potential, right? This is what we call as the potential difference between A and B. So this is VAB. Potential difference between A and B. Got it or not? Earlier if you take it from infinite, then actually we define that as the potential. So there is no difference over there. But here actually there is a difference because you are trying to compare two different points. Earlier actually you are trying to compare with a standard reference which is at infinite. So that's where we assume as the zero potential. Got it or not? Now if you understood this one, so on your own try to find out the potential difference between two different points of a line charge. So there are two cases. Here actually let us say I have a line charge like this. Now just draw a circle around that line charge. Now I am trying to move from here to here on the same circle. What is the potential difference between A and B? That is one question. And another question is, now actually I am trying to move from this particular point B, which is at a perpendicular distance of B, to a point which is at a perpendicular distance of A. So this is how actually I am trying to move. Or actually I wanted to find out the potential difference between A and B. So this is A and this is B. So can you find out for a line charge? This is a line charge. So of magnitude rho, coulombs per meter. Find out the potential difference between AB in this case and between AB in this case. What is the value in this case? What is the potential difference between VAB? Anybody? In this case, what is the potential difference between A and B for a line charge of magnitude rho coulombs per meter? Anybody got? Hafiz? Ranjana? Anybody else? Okay. So rho by 2 pi epsilon into log of B by A, that is case 2, that I agree. But what is case 1? So this one I am asking. This actually most of the people you might have done. But I am asking this one. Okay, so let me solve this. See this, the electric field intensity at any point of an infinite line charge is always equal to E is equal to rho by 2 pi epsilon r into r cap in cylindrical coordinate system, right? Got it or not? Now in cylindrical coordinate system, yeah, 0 for case 1 is correct. See this, in cylindrical coordinate system, DL is this one, the second one, right? Now this r cap is there. Now if you wanted to find out the potential, V is equal to minus integral, right? So A to B rho by 2 pi epsilon r cap dot DL, right? Now DL component which is moving, right? So this is actually r d theta theta cap. There is no dr component, there is no dz component. That means there is no movement along z direction, this is dz direction. There is no movement along this direction, this is dr direction. So this is equal to 0 and this is also 0. but only movement is in the phi direction. So that is a magnitude of, if this length is r or actually a, then a into d phi cap. This is actually the elemental component that is moving in this particular direction. Got it or not? Right? So here actually dr0, dz0. In this actually dr0, dz0. That means r d theta theta cap is left over. So here actually dot product with r d theta theta cap. Now the dot product of r cap into theta cap. R cap is in this direction and theta cap is tangential to this direction, which means that there is a 90 degrees angle between these two vectors, which means the dot product of these two are going to vanish. So r cap dot theta cap is equal to 0. So this entire integral will go for 0. That means there is no potential difference between these two, right? Which essentially means that, so potential is a point function, because this is equal to VA minus VB is 0, because this is 0 and this is 0. Got it or not? So, sorry, the potential is there. This is the same magnitude, VA minus VA. This is equal to 0. Whatever the potential that is there at this particular point, the same potential is there even here as well, because both are located at exactly same distance r or a. Got it or not? So there is no potential difference in the circular fashion. But in case of this one, this will become dr r cap. This is the second case, because here there is no circular movement, there is no vertical movement, right? So only movement is horizontally from a distance of b to for a distance of a, right? So there is a horizontal movement. Now in this case, so dr into r cap, right? So this dot product will become 1, and finally this is equal to minus, or let me erase this, integral minus, so b to a rho by 2 pi epsilon r into dr. Rho by 2 pi epsilon r into dr, because r dot r will become 1. So this dr is left over. Now actually rho by 2 pi epsilon log r. So this is minus of a to b, right? So log a minus log b, or if you bring the minus to the inside, log b minus log a. Rho by 2 pi epsilon log b minus log a, or rho by 2 pi epsilon log b by a. So this is the potential difference between the points b and a in case of infinite line charge. This is very, very important for us in case of calculation of cables performance. Electric cables will be there, right? The capacitance associated with an electrical cable is decided by this one. Got it or not? Right? So actually how the capacitance is calculated in this case is, now actually I hope you understood this one, you just note it down. I am going to explain how the capacitance is calculated from here. Let me know once it is done. Fine? In first case, right? So there is a Q charge, point charge. For this actually we have calculated the potential is equal to V is equal to how much? What is the potential value? Q by 4 pi epsilon R, right? Q by 4 pi epsilon R. Now, we know that Q is equal to CV or C is equal to Q by V, right? Now, if you bring this to this side, Q by V is equal to 4 pi epsilon R. This is equal to C. Q by 4 pi epsilon R is nothing but the capacitance C. Got it or not? Which means that suppose if I have a point charge here, and if you consider any charge or any random surface which is in the spherical shape of any radius, now the actual capacitance associated within that sphere is given by 4 pi epsilon into the radius of the sphere of assumption. Now if you take R is equal to infinite, then that is infinite capacitance because R is coming in the numerator, right? Now if you take the other case, if you take a line charge, suppose I have a line charge. So this line charge is nothing but actually, this is actually carrying charges, right? Which means that because of the flow of current or because of the flow of charges, there will be an inductance associated with it. At the same time, in this particular line, right? So in this particular line, let us say I have a cable with a dielectric. So this is the dielectric or actually the plastic cover which we will put it for each and every wire, right? So this is actually the cable design, let us say. Now in this cable design, so I have one more layer here. Usually the way it is asked is, it is at a radius of A and this is at a radius of B. What is the capacitance associated because of this cable between these two? This is nothing but the potential difference VAB you need to calculate first. This is what actually we just calculated. This is equal to rho by 2 pi epsilon into log B by A. This is what we have calculated just now, right? For a line charge. This is actually infinite line charge. This wire is nothing but infinite line charge. Now actually for this the potential difference is this one, which means that rho by, so this is the Q is equal to CV, C is equal to Q by V, right? So that means rho by VAB is equal to 2 pi epsilon into log B by A. This is coulombs per meter and this is volts, right? So this is actually farads per meter it will come. Earlier actually it is in coulombs. Now it is coulombs per meter. That means you will calculate the capacitance per meter length, right? So that's why it is farads per meter. So this is what is the cable capacitance we calculate. In long transmission lines, when we calculate in power system side, this is what we use. Got it or not? This is actually very, very important formula in case of power systems calculations. So line constants, we will be using this. Any questions? Any questions? Fine. So these are some of the important concepts. Why are we calculating rho by VAB? Okay. See this, actually the capacitance by definition is Q by V. Capacitance, right? It's a constant and it is like actually, so why it is coming this way is, suppose, let us say this is a parallel plate capacitance. Now actually I am trying to inject certain charge of magnitude Q here. Now I have filled up this entire thing with a dielectric D. Right? So this is the dielectric I have filled up and I have applied a charge of magnitude Q. So what it will do is, it will try to induce opposite charge minus Q magnitude here irrespective of this particular dielectric. Right? Now the relation between these two is automatically if there is a positive charge and if there is a negative charge, there will be a potential that will be associated between these two. Got it or not? It will try to do some work and it will try to do some work, right? If you bring in one particle here, maybe a charge of magnitude 1 coulomb, so this will try to attract and this will try to repel it. Got it or not? Understood or not? Ranjana and Hafiz. So randomly if you are putting a charge here, what it will do, this plate will try to attract it and this plate will try to repel it. That means essentially it is trying to move there and then trying to associate there. Now, if there is a potential difference that is accumulated between these two, and automatically that potential difference is just dependent on this Q. Got it or not? Or anything else it is dependent? If I increase more charge here, automatically it will induce more negative charge here. That means the potential difference is going to increase again. That means the potential difference between these two VAB is directly proportional to what I am applying in. Got it or not? Right? So rather than VAB, if I say just V, so this is Q is directly proportional to V. Right? Or Q is equal to, remove the constant there. Remove the proportionality and replace with a constant C. Or C is equal to Q by V. This is a fixed ratio. That's what I am intended to say here. This is always a fixed ratio that is just dependent on this particular Q. The potential will automatically increases the way you apply here. If you apply lesser charge, the potential will be less. If you apply more charge, the potential will be more. Got it or not? Now, there is a direct relation between these two and there will be a constant ratio automatically that comes in Q by V, which we call as C. And that's what we define as the capacitance. This capacitance is just dependent, this constant value is dependent on the physical parameters of this arrangement. So how much length is there and how much width of the plate is there, how much distance between these two plates. So all those things actually governs that constant value. And this constant we define as the capacitance. Right? Now actually any random situation if you take off, where there is a charge involvement is there, automatically the potential is going to induce there. Automatically the capacitance will be associated with that particular relation as per this one. Got it or not? Suppose if I have a point charge of magnitude Q here. Now if I randomly put a shell like this, and entire thing is actually built with air. Inside actually there is nothing. So this is, let us say, one plate, iron plate. So this sphere is an iron plate. There is a point charge in between, exactly at the center. So entire thing is filled up with only air. So this air will act as a dielectric. Now what it will do, because of Q is here, it will try to induce minus Q here. There is a dielectric associated between these two. Automatically there will be a potential difference. We have already calculated that potential difference between these two, which we have calculated as V is equal to Q by 4 pi epsilon into A. So let us say this is the A length. That means the capacitance associated with this particular charge between this charge and this particular sphere is given by 4 pi epsilon A, which is equal to Q by V. Got it or not? And that is dependent on which kind of sphere you are assuming. Is it lesser radius or more radius or infinite radius? That depends on up to you. So that is actually the physical parameters that will decide that constant. Got it or not? Automatically this A will be deciding, right? A is equal to, so this is equal to C, 4 pi epsilon A. That means A is the radius of the sphere you are assuming. That is actually the physical dimension. Got it? So any other questions, Ranjana? So here actually, in case of line charge, what we are doing it here is, the charge actually we are expressing, suppose infinite line charge means infinite charge is there. Will it make any sense for us, our calculations? Infinite line means infinite charge. Because you are trying to distribute throughout the charge for infinite line. Which means that for our calculation purpose, you have to express the charge in terms of coulombs per meter. So per unit length, how much charge is associated? That is exactly the parameter that you need to be defining it. Now here, so rho coulombs per meter you are putting it here, right? Rho coulombs so coulombs per meter you are putting it here. Automatically, whatever the calculations you do, it will come per unit length. So here coulombs per meter, that is why farads per meter is the capacitance. Got it? Okay. This is about the potential, right? Okay. So now coming to the Gauss law. Right? So this Gauss law is mainly to calculate electric field intensity So this is mainly to calculate electric field intensity. So why this is coming is, actually we have calculated electric field intensity with the help of Coulomb's law. But there we are trying to involve lot many vector quantities. That's where the complexity is coming. That's what we have discussed, right? But this Gauss law, what it will do is, by giving a theoretical definition, it simplified a lot of calculations. So that's the beauty of this Gauss law. What it says is exactly whatever we discussed now. See this. Suppose actually I have a charge of magnitude Q which is placed on this particular sphere, let us say. So this is an experimental law, right? So Faraday conducted an experimental law. So here he is trying to put one more sphere here. So let us say this radius is A and this radius is B. And he tried experimenting it by keeping a charge of Q here. And is there anything that got induced here? Right? Now, here actually automatically it will induce the opposite charge, right? So minus Q is induced here. Now, here actually entire thing actually he will fill up with some dielectric. So irrespective of this dielectric material, whatever he put here, right? So there will be a charge that got induced on this outer sphere. Got it or not? And the magnitude of the charge is Q here and here it is minus Q. Got it or not? Suppose I keep one more sphere like this. So remove this original sphere and then try to keep one more sphere like this. Now let us say this radius is C and it will try to induce the same here. But if you notice, the area of this sphere is different and the area of this sphere is different. Got it or not? The area of this sphere is different. The surface area I am talking about. The area of this sphere is completely different. But the same charge is distributed throughout. The same charge magnitude is Q only. It is distributed throughout. Right? So the influence of this particular charge that is getting affected onto this particular sphere, right? So this is what he defined as the flux. So flux is nothing but the influence only. So this is the influence of this internal charge on the outer sphere. That influence actually he defined as flux. And this he said that this is defined as phi and which is equal to Q because the same magnitude of Q is actually getting induced here also. That means the influence is same. Whatever the charge is here, the same charge is getting induced here. That means these two are equal. So that flux, whatever he defined, he said it is equivalent to the charge. Got it or not? That is the basic definition he gave it. Now here, if it is the flux is equal to the charge, then automatically the next question is, here the same Q is distributed throughout the sphere. And here also the same Q is distributed throughout the sphere, which means that the surface area of this sphere is 4 pi epsilon r square. Sorry, 4 pi r square. This is the surface area of any sphere if your radius is r. Now for this particular sphere, the radius is b. That means the distribution density is 4 pi r b square in case of this sphere 1. So this is actually D he defined. Charge distribution density. This charge is distributed throughout this spherical area. Got it or not? D is equal to Q by 4 pi epsilon b, 4 pi b square. Now in case of this second sphere, again if you try to calculate in the second sphere, the same charge is distributed for an area of c square. Because this radius is c. Got it or not? So what he is trying to do is, he found out the entire surface area and the same charge is distributed on that entire surface area. So then Q by 4 pi c square is nothing but the charge distribution density. So actually density usually we apply for 3-dimensional figures, right? So whatever that got filled up in the complete volume, that's where actually we apply this density. But here in this case in Gauss law, we apply for the area. That's the difference, right? We apply. So distribution density is actually area distribution density we mean here, right? So that's why Q by 4 pi c square. Suppose if I randomly select a radius of r, then it is equal to Q by 4 pi epsilon r square, 4 pi r square. This is actually the charge density distribution. Q by 4 pi epsilon r square. Right? But we have already calculated with the help of Coulomb's law, E is equal to Q by 4 pi epsilon r square. This is E. Got it or not? And if I bring this to here, Q by 4 pi r square. So this is what is equal to D we have defined here. Got it or not? And here if you notice, this Q by 4 pi r square, here actually we didn't mention any direction. But here actually Q by 4 pi epsilon r square r cap is the direction. That is why when we calculate the surface area, we have to consider the perpendicular area. Perpendicular area. That means the electric flux that is coming out of this particular charge is coming exactly in all the 3-dimensional ways, coming out of a, let us say a ball is there. In the middle of the ball there is a charge. In all the directions the radius vectors are coming out, which means that those are the flux lines. These flux lines, if you notice at any point of the surface, it is always coming perpendicular to that particular surface. Got it or not? Understood or not? It is always coming perpendicular to that particular surface. Right? So here, even here also in case of point charge, the electric flux lines are coming exactly perpendicular to this particular surface. Right? Hence these two are equal. Right? So this is equal to D. So that means there is an important relation, D is equal to epsilon into E. This is a new relation that got derived. Clear? Right? The limitation of Gauss law is it never tells about the direction of electric field. So this is the limitation. So that's why when you talk about Gauss law, first of all you have to know how the flux is coming out or how the electric field intensity lines are. Got it or not? Understood, Hafiz? Fine. So this is actually the Gauss law, right? Now here, suppose with the help of Gauss law, I wanted to find out the electric field intensity for a point charge. How? Just see, as per Gauss law, D is equal to Q by 4 pi R square. And D is equal to E into epsilon is equal to Q by 4 pi epsilon R square. Sorry, 4 pi R square. Or E is equal to Q by 4 pi epsilon R square. See how simple it is. Earlier what we did? We applied Coulomb's law. And then we tried to derive all the vector quantities. And from there actually we tried to integrate it. And then actually finally found Q by 4 pi epsilon R square. Now it's a matter of, by looking at the diagram itself, you can make out what is the electric field intensity. This is the beauty of the Gauss law. But the limitation is, you have to be aware that the electric flux lines are coming exactly radially in all the directions of the spherical. Right? So that is the limitation. Now actually, if you take line charge, this is a line charge. Now, randomly imagine a surface, a closed surface, which is closing this particular line. So this is actually infinite to minus infinity. Now actually I have just assumed this way. This is a cylinder. So this cylinder, so this is cylinder. Now the electric flux lines are coming in this direction. Let us say the imaginary surface at a distance of r from the line. So this is r value, right? Now this length where I am assuming the surface, let us say this is L, right? L. Now the electric flux lines that are coming out perpendicular to this particular surface are, right? So this is spherical surface, cylindrical surface is one surface. And the top surface, so this is actually A1, this is A2 and this is A3. There are three different surfaces are there. Now I take the total flux that are coming out of this particular surface is, so the flux lines that are coming from A2, right? So the flux lines that are coming from A2, how much? So we have the relation, so Q by 4 pi R square is equal to D, or this can be written as Q is equal to D dot S. S is nothing but the surface area. Now here this length is R and the surface area is pi R square, right? And then the electric flux lines that are coming out of this particular D, how much? So perpendicularly there is nothing coming out, right? So this is 0. And perpendicularly that are coming out in this particular direction is again 0. Right? Only electric flux lines that are coming out is perpendicular to this cylindrical surface. Got it or not? This cylindrical surface area is how much? 2 pi R is the length and length is the height. So this L into 2 pi R, that is the actual area. This is enclosing, so this particular surface and the electric flux that are coming out. So this is actually right hand side. D dot ds is equal to the total charge that is closed with this particular surface. So what is the charge? This length is L and the charge density is rho coulombs per meter. Now the total charge is rho into L. And the dot will vanish because the angle is 0, because the radius is in this direction, right? The normal of this particular surface is in this direction and this D is also in this direction. That means this is equal to 2 pi R L into D is equal to rho into L. And this L will get cancelled. D is equal to rho by 2 pi R, or E is equal to rho by 2 pi epsilon into R. Got it or not? Rho by 2 pi epsilon into R. So you have calculated with lot many integrations, the complexity went away with the help of Gauss law. Simply by just imagining a random surface which is closed in nature, and you tried calculating the total charge which got enclosed by that particular surface, and then that is equated to the electric flux lines that are coming out of that particular surface perpendicularly. This is what Gauss law says. Got it or not? So total charge enclosed on one side and the total flux that are emitting perpendicular from the surface on the another side will directly give the relation for the electric field intensity or the electric flux density. That is the beauty of Gauss law. But here, so you are assuming that the electric flux is coming in this direction, there is no coming here, there is no flux coming in this direction. You are telling you upfront. This information, if you know, then only you can apply Gauss law. This information won't be given by Gauss law. Again, for that you need to depend on Coulomb's law. Got it or not? So that is the limitation.